Hello and welcome to the lecture on advanced ray tracing, which is a lecture within the series of computer graphics course at KAUST. We have already discussed the ray tracing in its simpler form in earlier lectures, and today we will be adding some complexity to the already learned basis in order to achieve a more photorealistic appearances of various objects or effects. The first effect which we will be describing is a refraction. So, meaning that light will be transmitted through a medium, through an object, and not only reflected. We already discussed the reflection of a light ray from an object on a lecture before, and today we will be adding to that the aspect of refraction. So for certain objects, which are also called dielectrics, we will be basically dividing the light energy upon the incidence on its surface into part which will be reflected and a part which will be refracted. We can also model it with a part which is simply absorbed or transformed into other forms of energy, but for now we will be talking about reflection and refraction. So if we are looking at this drawing here on the right hand side, we can see that our light is coming from the direction D here, and it will be under a certain angle, theta, here, which is spanned between the vector D and the normal vector, or should I say minus D and the normal vector. This light direction can be used for computing the reflection vector. As we know, we already know how to compute the reflection vector, which will be also spanning the angle theta with the normal at the point of the incidence of the light ray with the surface. The new thing here will be that we will be now also refracting a certain part of the energy of this ray, and the refraction will not go in the same direction as we would expect, but it will be the light ray will be bended at the point of incidence. So we will have here a new angle, which is not the theta anymore, but the angle phi, under which the new light ray within the medium will continue along its traversal through the medium. So now we need to understand how can we find the relationship between the angles and this the one which is the incident angle theta and the refracted angle phi. So this can be modeled by the so-called Snell's law, where the sine theta and sine phi are related to each other through the so-called refractive indices of their respective materials. So the refraction index of air is 1, and the refraction index of water is 1.33, because you can see that this is a dielectric which is transparent, and if we can experience this refraction effect if we, for example, are going out, let's say on the sea, and we would like to paddle, and we see that our paddle is somehow looks in the water as being positioned under different angle, or it looks like kind of broken, but we know that it is not broken, but simply the light rays are bended at the surface of the water, which causes this weird effect that our straight pedal is now looks broken at the surface of the water. Then glass would have even higher refractive index, and the very high refractive index is associated with the diamond. So we can express also this Snell's law in a slightly different way as n divided by nt. So these are the two refractive indices of two different dielectric materials. And here we will have is equal to sine phi divided by sine theta. If we will continue with our ray, which is transmitted through our semi-transparent material, at some other point of incidence, we will again come to an interface between two materials, and at this point, we again will perform a reflection and refraction. So within our object, we will be reflecting the ray, and this reflection will be by the angle phi, because that was the angle of incidence at the surface normal. And then we are again bending the ray, and the ray bending will be bent again, actually, by the angle theta, which we also can observe, which we can also observe here. So what will be the result of such a traversal of a light ray through such a brick of glass, if you like, that there will be the same, the light ray will proceed in the same direction, which has been transmitted through the glass, but it will be slightly offsetted. So you can see here that this ray will be then parallel to this ray. So this offsetting is caused by the refraction and based on the particular refractive index of the material which we are dealing with. Now, how can we capture this geometrically? So if we look at our scene, we can express we can simplify the geometric situation by considering just a two-dimensional case. This two-dimensional case will be defined on the plane, which is defined by the vector d, and the normal vector at the surface. So we are in the plane spanned by these two vectors, and we can calculate the theta, for example, angle, and this angle theta can be calculated as minus d dot n will be the cosine of the theta. So cosine theta is equal to dot product of minus d n. And we can also calculate the reflection vector, but the question is, how can we calculate what we want to calculate is this, which is this new aspect. What is the direction, what is the vector of the refraction? The vector t. So we can see that the vector t is can be defined by from considering this as a as a right angle triangle, here, for example, and the vector t being the hypotenuse, we can calculate the um, the component in one coordinate through the sine function. So sine is defined as the fraction between the uh, the opposite side, which would be this one, is the opposite side, to the hypotenuse, which is our t. So and uh, the so from this we can see that sine is uh, basically expressing the projection of our vector t onto the vector b. We will come to what is the vector, how to calculate the vector b in a moment. But you can see that this direction where we have our opposite side is parallel to the b. So the projection is on the same vector orientation. So here we have the sine phi, which scales our unit vector b, and there we get one coordinate. And the other coordinate we can obtain from cosine phi. So again, we have the angle phi, and we are calculating the adjacent side ratio to the hypotenuse, which is the definition of cosine. And this from this we can therefore get the other part of our vector t, which is scaling the normal vector, negative normal vector, should I say, because we are now having the normal vector minus n would be here. And the scaling is then telling us how much of the vector n by the cosine phi, how much of the vector n contributes to the vector t. So, and the sum of these two scaled vectors in this coordinate space Bn is expressing us the vector t. The vector d, on the other hand, can be modeled in a similar way, because we can see that it is again the one component of it is modeled by the minus cosine theta, so not the angle phi or phi, but the angle theta. So this will be the which is the opposite adjacent side to the hypotenuse. Now our hypotenuse is this one, and we have here again a minus sign because we actually are having a d pointing this direction, and we would this way, if the n would be, if here would be plus, we would be calculating the d in the opposite direction. So this minus is changing just the direction. And then, so this is the cosine part. We already know this component. And now we need the opposite component. And this opposite component is can be calculated again as the sine of theta and multiplying the vector b, the basis vector b here. So we have calculated now t and d, but we already know d. So this is our input. N and d are our inputs. What we, however, do not know are, and we also know the theta. What we do not know is the phi vector, is the t, and actually also the vector b. So we express the vector b as a from this equation, and now we have an expression of b which we can plug for the calculation of the vector t. So here you can see that we are now putting the b, and we actually create the fraction between sine phi and sine theta here, because the sine theta comes from the b, from the denominator, and the sine phi is already in the original equation for our vector t. So we have this fraction here, and then we have the rest of which expresses as the vector b. Nice. And you can also see that this sine phi divided by sine phi divided by sine theta is actually equal to from the previous slide n divided by nt. So we can is equal to, not minus, but is equal to n divided by nt. So we can plug it in instead. Then we do not have any signs here. We actually do have the cosine theta here, and we also said that the cosine theta can be expressed as minus dot product of minus t and n. So this is what we are plugging it here. That's why the sign is changing here from plus to minus. And then we have one more thing here, that the vector t is having the cosine phi here. We still don't know this. What is the cosine phi? Other than that, we know every aspect of our equation. So the cosine can be expressed, we know already the equation that sine squared x plus cosine squared x equals 1. From this, we can express that the cosine x equals 1 minus sine square x, and in square root out of that. So that's what we are putting in here. Does it help us? Yes, it does, but we still have this unknown phi here, which is a little bit inconvenient. However, we can express the phi by sine phi is equal to, what is it equal to? Sine phi is equal to n divided by nt times sine theta. So now we can replace this term instead of this sine term here, and now we know everything. However, the theta we do not know directly. We can compute it directly, but what we know is it's a cosine theta, which is minus the n. So what we can do is this is also equal to n divided by nt, I will change the color, times, and now square root of 1 minus cosine theta squared. That would be the expression for our sine phi, and that is equal to n divided by nt, times square root of 1 now minus dn and squared. So now it was the cosine was minus d dot n, but here we are, we can put it there, minus dn squared. So this is our now equation for calculating the vector t. It looks a little bit complex in one hand, but on the other hand, we have expressed everything just by vectors. We do not have any angle here anymore, and from this, from the vectors and the refractive indices, we can simply compute the refractive, the angle or the vector under which the refraction is happening, the vector t. Now we are coming to an interesting aspect, because sometimes we are, if we are performing, and so imagine we have two materials, and we have one normal here. If this is our incident light in this direction, and the n and nt is here, while nt is bigger than n, then this angle, I don't know what will be exactly the angle phi, but it will be the phi will be smaller than theta. Here is the theta, and here is the phi, or phi. So this will be always smaller if the refractive index of the new material or of the internal part of the material is higher than the surrounding. But if we go the opposite direction, let's draw this again. If we go the opposite direction, so we have an, let's say, a block of material which has Nt as a, which is bigger than n. No, this is Nt, which is bigger than n. And our ray is sort of going this way, let's say. Then this angle, phi, is still smaller than the angle theta. So at some point, so angle theta is bigger than phi. And at some point, for certain phi, our angle theta will be 90 degrees, will be actually on this surface in the same direction as the surface is. And for angles which are even bigger, for phi, here, there is actually no refraction. There will be only, all the light energy will be reflected. So nothing will go out. And this effect is actually called total internal reflection, that out of this material, no light goes out and it is reflected back within this material. This is actually the basis, the foundation for optical cables, where we have a certain dielectric material which has a higher refractive index than its surrounding. And this higher refractive index is then causing that all light directions under certain incidence will be completely reflected within this dielectric material, and nothing will be refracted outside. So it is a great effect for optical communication. Now, how can we find out that the total internal reflection is happening? We have here, you remember, we had in our previous slide the expression for the cosine phi, which we expressed then as 1 square root of 1 minus sine phi. squared. And if this square root is negative, then if the square root is negative, then we have this total internal reflection effect. There is no refraction happening. But you might ask yourself, why would this be negative if there is a sine squared phi? This sine should only go between 0 and 1 or minus 1 and 1. Well, keep in mind that this sine phi is calculated, sine phi is calculated as a n divided by n, nt cosine, sine theta, and if in case now we are inside, then it will actually be the n will be higher than nt. So n is higher than nt because we are inside. So let's say n would be for diamond and nt would be for air. So this term is now actually expressing something which is not really a sine, because sine really cannot go between minus 1 and 1, and therefore it will be an expression which will be higher than 1 and will cause a negative value here, which will then mean that this doesn't make sense. And in that case, we will find out that there is no vector t existent because there is a total internal reflection happening. But in case this is not happening, this is not the case, we need to, while we have now calculated the vector t and also the vector r, the reflective direction, we need to calculate how do we split the energy, the light energy, between refraction and reflection. And this can be modeled by the Fresnel equations, and the so-called Schlick approximation is a good way to model this effect. Here we have the various terms. For example, the R0 is the reflection when our light direction will be completely aligned with the normal vector. What will be the reflectance at normal incidence? So this is the R0, and that can be computed as from the refractive indices of the two materials, Nt and N. In the book, instead of N, you will have here 1 because it assumes air. But in general, this will be N as the material from which the light is coming from. So this way we can compute the reflectance at normal incidence, and based on the angle theta, so the angle theta is the one of the two angles which is bigger than the other one. So it's the higher angle one of those two is the one which is sort of scaling this the fraction of the reflection. So if our theta will be 0, so theta is 0, so there is exactly the light direction is at the normal direction, then this term will be 1. So this term cosine phi will be 1. 1 minus 1 is 0. So this second term will be then equal to 0. and we have the reflectance at normal incidence. The other example which we can make is that cosine phi is, let's say, equal to 1. No, phi is equal to 90 degrees, which will be cosine will be 0. So this will be 1. And then we have here R0 plus 1 minus R0. So the reflection will be 1. There will be, everything will be reflected. Obviously, if our direction of the light direction will be 90 degrees to the normal, then nothing will be transmitted. Okay, so this is the amount of how much light is reflected, and the amount which is refracted is 1 minus this term. We can see this in the pseudocode, in the following pseudocode here. However, before that, there is one more point aspect to deal with, and that is the attenuation of the light energy. So far, we have neglected this term. We have not really attenuated the light energy, but in some dielectric materials, the light is being attenuated as it is passing through this material. And this attenuation can be modeled by this differential equation, where at the change of attenuation is proportional to a certain constant C. If we look at this differential equation and we solve it, we can see that this is the solution of the differential equation, where we have some unattenuated light intensity I0, and this attenuation is then controlled by this exponential function, where the x would be the distance which is being made. If we, for example, measure a certain attenuation after a unit length, let's say the attenuation value will be A, then we can define that the intensity at a distance, or of a unit distance 1, will be A times the original intensity, and from this we can infer that the minus C constant will be equal to ln So our final attenuation function will be Ix based on this attenuation constant, which we can measure after some unit length, will be equal to I0 E powered by ln A and X. Okay, so this would be how we can attenuate our intensity, and based on how long is the attenuation going, how long are we passing through the dielectric material, the more we will be attenuating. We will be seeing this in the following code, which is describing this refraction and reflection of the light ray. So in our ray tracing, we will be going from the viewing direction, and we will be hitting certain point P on the surface of a dielectric. And this point P, at this point, we would like to then reflect certain part of its light energy and refract, or we are now going in the viewing direction. We are not going from the light, but from the viewing rays. So we are splitting these viewing rays into the reflected secondary ray, R, VEC, and the refracted one. So the reflected ray can be computed based on the D vector, the vector D, which we had previously on our geometrical illustrations, and the normal vector. We know how to calculate it from the previous lectures. Now, if the dot product between D and N is smaller than 0, this means that we are coming from a smaller value dielectric into a dielectric with a higher refractive index, meaning that we will be for sure refracting. There is no total internal reflection happening. And therefore, we are calculating the refraction in order to calculate our vector t, which we have calculated in the geometrical sense on the previous slides. Then, furthermore, we will be calculating the cosine of theta here, which we will need later on in order to be able to split the light energy based on this Schlick approximation. So we are calculating this cosine value, and afterwards we will be assigning to our attenuation constants a value 1. Because there is no attenuation, we are coming from the air into some higher dielectric with some higher value. The else part here is expressing going from the material with a higher refractive index into air. So we are in the else part, we are in the glass or diamond, and we are at the point P, we are reaching the interface to air, for example. In such a case, we need to calculate the attenuation of our previous ray within this material. So our K attenuation coefficients for each channel R, G, and B will be calculated here as we just learned it from the Beer's law. So here is an exponential function of ln A, which is now a term which is defined for each color component separately, and we multiply it with the distance which has been already traversed with our ray to reach the point P. And this attenuation is then used later on. Now we have the possible situation that we could have the total internal reflection, which would mean the else part here. So in such a case, if we have total internal reflection, so we are not leaving our diamond or glass in which we are already in, we will now return this color function after we are reflecting. So we are now reflecting from this point P, and we will be then calculating an intersection with another interface, and there we will have our a new value for the T here. And we are modulating this color, we are attenuating this color with the K coefficient, which is calculated for each color component. So this is a component-wise multiplication here. If, however, there is no total internal reflection, so this term will return true, then we will simply calculate the T-vec. So this is the vector which goes, how are we now leaving the dielectric with a higher refractive index, and which direction is our ray continuing after the refraction. And we will be computing here again the cosine term, because we are computing the cosine term from the dot product with the where the angle is higher. Once we have computed that, we are ready to split the light energy into R 0 and so calculate the R0, which is calculated as we had it before, expressed on the in the formula on the slide earlier, and then we are computing this light energy fraction, which of the light which will be reflected. Once we have computed it using the previously computed reflectance at normal incidence, then we will be performing a refraction here, with again computing the new T value for the new ray which we are emanating. So this is reflection, and we are weighting this reflection with the amount of light energy which is going to be reflected. And then for the refraction, we are having the 1 minus R term, which we weight in a perform a component-wise multiplication of the value coming from this function color, which is further evaluating the color after intersecting another position once we follow the vector T-vec, the refracted vector, and at some position T, new T value, we will then have an intersection with the surface again. And this whole will be then scaled component-wise with this attenuation coefficients K. Again, a component-wise multiplication, so perhaps the star should have been here. Hopefully this has been clear. This is how a refraction can be added on the top of reflection and to model dielectric materials which are semi-transparent, in which also the light energy is being attenuated. Another interesting aspect of advanced ray tracing is the concept of instancing. In here, we will be dealing with one basic object and then many instances of this basic object, which are each individually transformed. So, for example, you can imagine to have a circle or a sphere in 3D, which is the essential building object, and then we will have transformations applied to this sphere, forming individual instances. So one instance, for example, could be that it's scaled in one direction and forming a ellipse, or in 3D an ellipsoid. It could be also, for example, rotated, or it can be translated. So all the transformations we have been dealing with can be applied to these individual instances. And these instances can be then populated in the scene many times. This has two advantages. One obvious advantage is that we will have lower storage requirements, because actually we are storing just one object in the scene and instancing it many times in the scene, and storing explicitly the transformation of each instance. The second advantage is that sometimes on the basic object, the ray tracing can be simpler to compute than on the transformed object. For example, if we will have not axis aligned ellipse, well, this will be a more complicated structure to ray trace than a sphere, for example, and find an intersection with a sphere. And here comes the interesting property, which you can also use in your assignment number 2. So in this instancing, either you transform the basic object to form the instance, and then you perform the ray tracing of this on this transformed instance and compute the intersection test with your rays, with your viewing rays, or other rays which are part of the ray tracing framework, or you do not transform the object, the instance itself, but you inverse transform the ray with the same transform which you would transform the object with the same transform, just inverse of it. You transform the ray and perform an intersection test with this inverse transformed ray and with the untransformed object. This will have the advantage, for example, in your assignment number 2, that you can transform, for example, an axis-aligned ellipsoid, but in reality, it will not be the object which will be transformed, but it will be the rays which will be the inverse transformed for performing the intersection test. So this concept of instancing can be used effectively also for the transformations, even if just one instance is used. So here we can see the principle in the illustration on the right. We can see that we have some original ray here, which is defined by the points A and B. For example, A could be the eye point, B could be the point on the screen as a pixel, defining the coordinate, center coordinate of the pixel. Now we have our transformed instance, which was originally a sphere, but it is now a transformed object into an ellipse. And this transformed object contains two intersection points with our ray, which are, for the simplicity, the points Q and R, but the transformed ones, M, Q, and MR, where the M is the transformation matrix for the instance. So instead of calculating the intersection test on MQ and MR points, or for the M transformed instance, we perform zero transformation on the object itself, but inverse transform the point A and the point B, and form the ray, which will be the ray with these inverse transformed points. Then we perform the intersection test with the untransformed object and compute the points Q and R. Obviously, these points will be somewhere different in space than the points MQ and MR. However, the value of the intersection parameter T will be the same. This will be the same, however, only if our vectors will not be normalized. So we need to make sure that we do not normalize our inverse transformed vector m minus 1a, m minus 1b. This vector should not be normalized. Otherwise, the consistency of the value t will not be the same. So once we calculate the intersection point, then we have the intersection point Q, and we can then transform this intersection point with the matrix M if we would need to. But perhaps we do not need to do it, because for the shading or for the distance, we just need the value t and calculate the distance, what will be the distance with the untransformed AB points defining the AB vector. This will be for defining the depth. But for the shading, we would need to define the normal. And here we need to keep in mind that calculating the normal is, after applying certain transformations, is a little bit tricky. Therefore, we will need to calculate the normal with this M inverse transposed matrix, as we had it defined earlier in the transformation matrices lecture. So this way we can perform instancing, which will help us to transform objects which would otherwise have much more complex definition, and we can define them very simply just as, for example, spheres, but represent with that axis not disaligned ellipsoids, for example. But it also applies to other objects as well. So we can see that transformation in one direction of objects corresponds to inverse transformation of the rays. And this can be often utilized in computer graphics. The next advanced topic of ray tracing is related to the constructive solid geometry. Constructive solid geometry means that with logical operations, you can construct more complex shapes out of simple primitives. So for example, imagine that we have set of geometric primitives, geometric objects such as sphere, box, or cone, and we would like to create more complex objects by putting them together and performing certain logical operators on them. Such as, for example, we can perform an union of two objects where in this case the circle and a square would be put into a union. This is very obvious. We can also perform a difference operator. So sphere minus circle. So sphere minus circle would be, square minus circle would be the square minus the part which belongs to the circle as well. So it will be simply this part, which will be the difference. The other difference will be circle minus square, so the entire circle minus the part which is shared with the square. And the intersection will be the object which has the common space shared between both of these primitives, both circle and square. Now, how this can be utilized in ray tracing? In ray tracing, we can perform the intersection test with all of these objects, all of these simple objects which form our complex object, and we can essentially create an interval between on our ray within which the ray is inside our object. As it is shown in this line of our ray, in the first on the top, we are defining an interval on where the t is inside the circle. So this would be the entire part within which is here the circle, the ray inside the circle. For the second one, we also define the intersection test for the when we are inside the square. And we can see that we are inside the square also on an interval, but this interval is just slightly smaller than the previous interval. And now we can, as we have these intervals defined, we can perform the logical operators on these intervals. Instead, on the geometry directly, we can perform it on the intervals of the ray parameters to find out what is the intersection with the ray. So for example, circle minus square in this second case will result in this geometry. And circle minus square would mean that we are subtracting the interval square from the interval for the circle. And we will end up with two intervals, actually. And if we are interested only in the first intersection point, the intersection point will be actually the same as with the circle in this particular case. If we would be interested to perform the square minus a circle operator, what will it end up with? It will end up, so I'm asking if we now perform the subtraction s minus c, what it will end up with. If you look at the two intervals, the C interval completely encloses the S interval and is even larger. So if we subtract it from the S, there will be empty set. And indeed, if we imagine what will be the object which is S minus C, so that object, I will draw it here on the top, will look like this. We can see that this object will be never hit by this particular ray. But if we will be interested in the intersection of square and the circle, then, for example, the intersection, the first intersection, will be this point. And this point will be easily calculatable from the intersection of these two intervals, t parameter intervals, and it will correspond to the point where the square is intersected, or where the square is hit. So we see that the constructive solid geometry can be very nicely realized in the framework of ray tracing by investigating the parameter t interval of intersections spent between the intersections and evaluating the logical operation of these intervals to find out the intersection points of these more complex objects. The second part of this lecture is dedicated to the so-called distribution ray tracing. Distribution ray tracing basically means that we are distributing more rays for capturing the physical light propagation, or to modeling the physical light propagation, than just a single ray. It should not be confused with distributed ray tracing, which will mean that we are performing a parallel operation of the ray tracing algorithm. So if we talk about distributed ray tracing, it means that there will be several computers or compute nodes calculating ray tracing. This is not what we mean by distribution ray tracing. This term means that we will be simply calculating more rays to to find out the particular value at a particular pixel. And this can be used, this concept of distribution ray tracing can be used for various purposes, for anti-aliasing, for soft shadows, depth of field, glossy reflection, and motion blur, as we will describe in the following. If you look at ray tracing as you have done it for the assignment number 1, you can notice that while the ray tracing results in beautiful images, they are a little bit edgy on the contours. We can see that the edges are in fact so-called aliased. There is this staircase aliasing, especially visible on the spheres, and we would like to somehow mitigate this problem. Well, this could be done by simply having higher resolution displays so that we cannot see the individual staircases anymore, so that our visual acuity is sort of combated by the resolution of the display, which will also lead to higher computational costs. Or we perform something which is called anti-aliasing, where we will not have a binary decision whether an object has been, or pixel is has been hit by an object, but we will have a more smoother transition, as can be seen on the contour of the sphere here on this magnification. How can this be achieved? Well, one solution is to perform a simple supersampling, meaning that our pixel, which normally is just evaluated by a ray traced through the center of this pixel, will be now evaluated. The ray tracing will be carried out through many points corresponding to this one pixel, to actually 16 points in this case. And this can be realized fairly simple. So instead of having for each pixel the just one ray to be sent, we have two internal loops, for one for rows, one for columns, and subdivide our pixel into 8 regions and compute the ray separate for these regions. And then we simply at the end average the color which has been achieved. For this, we will achieve the result as shown in this supersampling example, where some of these rays on the border of the sphere will become hitting the sphere, and some of them will be hitting the background. However, such a regular approach to anti-aliasing can sometimes lead to undesired effects. One such an example would be the moire patterns, which are originating from regular sampling, or other annoying patterns. That's why sometimes it is useful to break the regularity and perform more random supersampling. The random supersampling can be achieved in the following way. We are in the pseudocode, we again run n times n super samples, number of samples per pixel. But for each position, we are just assigning a random value between 0 and 1. So the I and j are the corner of our pixel, based on the definition either top left or the bottom left corner, and then we are sampling randomly this pixel area with samples. At the end, we are again performing the average operation of our colors. So here we sum up all the colors, and then at the end we divide by the amount of super samples we have created, we have cast. Another approach, which goes somehow both ways, is regular and random at the same time, is called the stratified supersampling for anti-aliasing, where for each pixel we will divide uh, the pixel into several bins, so to say, but will not be sampling its center position of the bin, but within that bin we are performing a random positioning of our sample, both in the X and in the Y direction. And then again, we will be here summing up the ray colors, and finally we will be dividing by the amount of rays we have cast through one pixel. Here, please keep in mind that every bin will receive just exactly one sample, which is for some reason strange that in this illustration, this one bin has no sample associated with, which is an error in the book. And there should be also some random sample placed there. So for the sake of correctness, let's put it there. Okay, so this is the way how we can perform supersampling in ray tracing with the distribution concept. The same concept can be applied to achieve different effects as well. For example, to achieve soft shadows. Normally, if we are having sharply defined borders between our objects and we have our point light sources, we will be also having in the scene very sharp shadows. So there will be no soft shadows as we can experience from our environment, where each shadow is very rarely very sharp, and this is only the case if the occluder is very nearby the occludee. So soft shadows are appearing, and the distribution ray tracing is again a good method how to perform a soft shadows effect. So one way how a soft shadow can be achieved is by defining an area light source just containing point light sources in some kind of array, and then performing the ray tracing and evaluating the illumination with respect to each of these light sources. This is possible to do. However, it will also result in some kind of artifacts caused by these discretized points of the lights. We don't want to have it, and we do not want to have these lights placed in a regular pattern as it is shown here. Rather use the similar concept as we used for anti-aliasing, also for the shadow rays calculation. So here we will define the points on the area light source again in the random fashion. Just to complete the discussion about the shadows, just that you know the terminology, the shadow is, for soft shadows, we are talking about umbra. Umbra would be an area which is always under full shadow, so its intensity will be completely dark, you could say. And then we have the transition between the umbra and the area not in shadow, which is the so-called penumbra. And within this area, the shadow is becoming less and less shaded in a linear way. But if we have such a line light source of constant intensity along the line as shown in this illustration. So back to our distribution ray tracing, we will be performing a computation of a position within the light source in a stratified way, as we did it for the anti-aliasing. And this way, we can then compute one of such positions as shown here. What we will do more precisely, we will compute different intersection positions in the pixel, and also which will result in slightly different intersection points with an object. And then also we will perform a search for each of these intersections. We will have a different point on the area light source to form the shadow ray. So that will be done in such a way that we are in, let's say, our area light source will be a rectangular area or parallelogram as shown here, and then we will define certain random values which will determine the position of the sample on this area light source. And this can be done. This would be the random sampling, the stratified sampling will be realized through some regular pattern or binning of these areas. For a pseudocode, you can see here that we will be creating two arrays of jittered points. One array will be used for the samples, and one array will be used for the points on the light. So in this case, you can see that the pixel defined by the indices ij in the screen space will be displaced by some value which is stored in this jittered 2D array R, and also for x and y. And then we will be using the S array for the positions on the light source. And then for each pixel, we will perform this n times, as you can see here in the pseudocode, and then we will normalize the value which comes out of the shading of the different intersections, and with different positions of the light source. This will end up into soft shadows. The next effect which we would like to deal with will be, and we can efficiently use the distribution ray tracing to simulate this effect, will be using the depth of field. Depth of field is an effect where we have a certain plane which is in focus, and other planes at the different distances from the viewer will be out of focus. This is happening for every optical system, including our own vision, that there is just a certain distance to which we focus on. This focusing in our eyes is based on the muscles which are stretching or relaxing our lens. However, and this will change the focal plane or the focal point of the lens, because the geometry of the lens will be based on the stress of the muscles, also changing its shape. So if we look at the concept of ideal lens, then an ideal lens which can be manufactured from glass, for example, has the following property. A parallel rays like this one and this one will be bent in with this lens so that they are ending up in the same focal point. And with these rays, you can also achieve another effect where at a particular position, you will, which at a particular distance on one side of the lens, you will have this object, so to say, sharply seen on another side of the lens at a particular distance. So you can see here that we have a certain object like this arrow here on the left hand side, and this arrow is there are several rays emanating from the tip of this arrow, but through our lens, which is here a very thin lens. This is a thin lens model which is used here. We will have its image of this object, of this arrow, sharp at a certain distance, where all these lens rays will be meeting. So, and at another distance, all these rays will not be meeting, and they will cause a blurred image of the tip of the arrow, either in front or after this position. We can see that the intersection is not at one point. So we can see that this object of an arrow through the lens will have just one plane in which this arrow will be sharp, or should I say the point on this arrow will be represented sharply. The model of the very thin lens in this case has the following property, that it for the line which goes directly through the center, the ray which goes directly through the center of the ray, there is no offset. You remember, if we have, from our previous discussion, if we have a certain ray, it will be then based on the internal refractive index of that of the dielectric. There will be some bending of the ray, and then again the ray will be bended, so there will be certain offset. But if we perform a thinning of this lens into minimum, this offset will be smaller and smaller. So there will be, in ideally zero thin lens, there will be no offset at all. So there is one property of this thin lens. Another property of the thin lens is that for lines which are perpendicular to the normal of the or actually which are parallel, for rays which are parallel to the normal of our lens, so the normal will be here. Those are defining us where is the intersection with our normal and those rays which are parallel to this normal, and their bent version after the lens will define us the focal point of the lens. And the same holds from the other direction for the lens which are so these two lens, the rays or lines, should I say, are parallel to each other, and the lens is bending this ray so that the parallel ray, so that it intersects through the focal point of the lens. So the focal point of the lens is a property of the lens which it characterizes it. So this is generally a discussion about modeling of lens and as an optical element. For our distribution ray tracing, we will use a simplified model of our lens in the following way. We want to simulate this depth of field, and therefore we will define a plane in which our objects will be sharp. So if we have our scene, let's say this is our eye point. Here we have our view port, and let's define another plane which will be the plane in focus. So this plane in focus will mean that all the um, rays which are sent will be all objects which are in this plane will be in focus, and the further away from the plane the objects will be more out of focus. How can we model this? So imagine that we have our raster in our viewport, and we are sending just one ray through the center of each pixel, and this ray will then intersect our plane which defines our focal plane. Then this plane which defines our focal plane is intersecting with our ray and forms a point. For this particular pixel, let's call this point a P point. Now, we will be creating something for the distribution ray tracing, which generates us more rays per each eye point, let's say. And so we will create a small neighborhood around our eye, and at each of these neighborhoods we will find some points from which we will start other rays, and we will connect these rays with the point P. And you can already see what is happening. These rays will be all meeting at the point P for this one particular pixel, should I say, only, which we originally went through and created the intersection with the plane. And all these values, all these lines are then are converging to this point and then diverging again. So for objects which are before our focal plane, this will be in out of focus, and for objects which are behind the plane, they will become gradually out of focus as well. So this way, by creating an array of eye points, if you like, we can create this effect where we define an additional plane of focus, find the intersection of the plane of focus with our original eye point and the center of the particular pixel. So we do this for each pixel individually, and then we perform generate other rays which are nearby our eye point and are also going through the point P which we have found. We can see it here on this illustration. Once again, it's just that the point P is changed for the point S, but otherwise it's the same concept. With this approach, we can generate interesting effects, and we can generate the depth of field, for example, as shown on this example from the book. We can see that the objects in the foreground, the glass and the bottle, are reasonably focused, while the background image of Mona Lisa is out of focus. We see also other interesting effects here, such as, for example, the offsetting of the chair. You can see that there is some kind of offset here happening between the chair. I will delete my mark so that you can see it clearer once again. And this is caused by the refraction effects. We can see here also interesting effects which are related to so-called caustics, which are here, which we will discuss at a later lecture throughout this course. The next effect, which can be nicely modeled with the distribution ray tracing concept, is to perform a glossy reflection. So we often do not want to have a reflection which is behaving like an ideal mirror. We therefore would like to have something which is a little bit more diffuse and not totally reflecting the ray in just a perfect mirror style. This can be achieved by performing the distribution ray tracing around the reflection vector. So imagine that we take the reflection vector r, which we have calculated, and then we define a plane which is perpendicular to this vector r and can be parameterized by the u and v vectors, which are both perpendicular to the vector r, and are sort of defining a small rectangle with a small neighborhood around the vector r. And then we can basically connect our point of incidence at the surface with the reflection neighbor points, which are neighbors to the ideal reflection, and we can cast several secondary rays into the scene in slightly different directions. And this will create us a more diffuse approach to ideal mirror, because there will be not just one direction, but there will be several directions, and then the contributions of these several directions will be averaged together. The last example of distribution ray tracing is related to motion blur. So we will be not, you see that all these effects are creating some kind of a blurring or smoothing. And so far, this blurring and smoothing was happening in space. But we can also use the same concept and perform motion blur in time. Imagine if we have a static scene where nothing is moving, there will be the motion blur will result in exactly the same scene as without motion blur, because there is no motion. However, if we have some motion, for example, a car is moving over time, and if we will take some picture of this car or a person, we can also experience that sometimes these objects are not sharp and are somehow blurry because the people were moving. So we want to make a family photo, and there is this one kid which is just moving its head. This is due to it will cause a motion blur, because during the exposure time, when the sensor was accumulating the intensities, this for the pixels, for some pixels, there was a non-constant stimulus. And we can model this also with distribution ray tracing, simply by sending rays through the same pixel several times over a certain time interval, and then averaging the colors of these rays. As simple as that. So you can imagine that we have this scene of the uh, of the of some balls where four of these balls are static and one is moving. And when we are performing the ray tracing, we will be, let's say, casting 10 rays per each pixel, but each ray will be sent at a different time. And at a different time frame, there will be a different position of this particular ball, which will be moving this direction. And sometimes we will perform intersection with the ball. Sometimes we will be performing intersection with the background because the ball has already moved. And this all will be then averaged and will be forming this blurry appearance of that object. You might think that this is undesired, but actually for motion picture, the motion blur is crucial, because otherwise the films are having a very strange stroboscopic type of appearance if they are perfectly sharp. So it is actually desirable in creating computer animations to create motion blur results, because those are actually such as we consider as normal images. So in the second part of this lecture, I was talking about the distribution ray tracing, which distributes several rays in space to perform several effects, or over time to perform the motion blur effect. Along with the other topics on constructive solid geometry approach for ray tracing, instancing, and refraction, this forms the advanced topic of the ray tracing. So this was all for today for the advanced ray tracing techniques. Thank you very much for your attention, and see you at the next lecture. Goodbye.